So let's start off by looking at case 1, where we're multiplying together a normal number with a normal number and getting a normal result. So an example of this would be 5 times 100, which would give us a value of 500. So I've done a cutout here of the multiplication from the tool that I've created. So we have the number 5 here, we have our value of our 100. So we could call our 5 the x value, the 100 our y value. And you can see that both of these are normal values, and I've also got them in hex here. So whenever we convert the bottom one here, we're going to get the bottom line here. So again, the best thing to do is always look at these numbers and try and convert them in your head if they're simple numbers like these. And you can see here we're going to have this number here, which is the exponent, so it's going to be 128 plus 1 is 129. We take away the value of 127, we'll have a value of 2, so it'll be 2 to the power of 2, which will be a value of 4. And we're going to multiply that 4 by this other part here. Now this other part here is going to be, well, that's a half, and that there is a quarter, so that's 0.5, and this is 0.25. But remember, it's going to be 0.25 plus the value of 1, because it's going to be a normalised value. So there's actually a bit here that you don't see, which is the 24th bit, which is assumed to be 1 because we're assuming the values are all normalised. So we're going to have 1.25 times the 4, which is going to give us a value of 5. So again, you can get through that with the value of 100 and you'll get this value here. Now whenever we multiply them together, we're going to get a value of 500, and this is the 500 in our single precision floating point number format. So let's see how we manage to get our value of 500. So we know that whenever we're multiplying, we multiply the mantissa and we add the exponent. So the exponent is going to be the simple part. So let's work through the exponent first of all. We're going to have our xe here at the bottom and our ye, and we're going to be working along this route here, working along here, and then adding, and then working along to get our exponent, and then working down to get our exponent in the binary format. So we're going to start off with xe. So as I said, xe there is going to be 129, so that's just the 128 plus the 1 is 129. We take away the 127, we've got a value of 2. We do the same with the y. It's 133 minus 127, we get a value of 6. We add the exponents, that gives us a value of 8. And finally, we add back on the 127 and we get a value of 135. Now there's another factor in here as well, and this little part here is called the bias. So in this instance, the bias is going to equal 0. But where do we get the bias from? Well, we get the bias from the multiplication of the mantissa. Now I've not shown the full multiplication here, we'll go in and have a look at it in a moment, but this is what we'll have done is we'll have multiplied out the mantissa here, which is really from this point here, so that's the 23 bits, but we would have also bit extended it by a value of 1, and again with this one here it would be 23 bits, and we would have bit extended this by a value of 1. Okay, so the actual mantissa here would be 1, 0, 1, 0, 0, and the mantissa here would be 1, 1, 0, 0, and so on all the way down. So whenever we multiply the 24 bits with the 24 bits, we're going to get 48 bits, and I've shown at the bottom here just the first few of these 48 bits. So these are the most significant bits of the 48 bits. Now the full stop, as I mentioned before, is going to sit at this point here. And we can see here in this instance that in order for the answer to be normalised, we have to start off with a value of 1. But we already have a value of 1 in this place, at the left of the full stop. So we don't need to add any other further bias onto this. So the final answer is going to be 135 plus a 0 is 135. And we convert that back to our binary, and this gives us this value here. And that's the value we see up at the top. And of course, what is going to be left over here as well from this point here backwards to the left is going to be our final value for our mantissa, which will be the 3, 1, 2, 3, 4 ones, 0, 1, and you can see that here. There's 4, 1, 0, 1, and it's all zeros the rest of the way along. So that's us done our conversion there. Now this is one case that we're going to look at. So this is going to be the case where we have a 0 and a 1. So what we can do now is we'll look at the case where we have a 1 and a 0, and we'll also look at the case where we have a 1 and a 1, and we'll also look at the case 0 and 0, although the 0, 0 case doesn't actually occur, so there's nothing to look at there. So let's go ahead and we'll look at this live in the tool. So we have the tool up in front of us now, so we can put in our 5 times our 100. Now we'll close that and we'll go and we'll have a look at it actually within Excel, and you can see here that I've worked through the multiplication. We've taken the 23 bits of our value here, which is our Y value, and we've bit extended it by a value of 1, so that's a 24th bit of the hidden bit, and we've done the same for the 5 and we've bit extended it. I've then worked through the full multiplication tree, so we're taking, in effect, look at this here, we're taking that line here and we're multiplying it by that line, the top line by the bottom line. So we're going to have 0 times all of this, which gives a value of 0, and then 0 times all of that. Each time we shift along 1 in, so it's just the same as doing a long multiplication. And then finally we add the columns up, and when we add the columns up, we're going to have our 24 bits times our 24 bits will give us 48 bits, and you can see it all the way to the bottom here. This is the least significant bit, and it works all the way along to the most significant bit here. And you can see here in this instance the most significant bit is going to give us a value of a 0 and a 1, and it automatically populates this little section here, which gives us the value for our exponent. So let's move on and we'll look at the next one where we get a 1 and a 0 in the top most significant bits. So we've got the second case here, case B, and the example we're going to have is 50 times 100, which gives a value of 5,000, and these are the values entered into the tool here, and our final multiplication here gives us this 32-bit value. Now the exponent here is going to be given by the 132 here for the x, and we take away the 127 gives us a 5, and when we do the same for the y value and we get 133 minus 127 gives us a 6, we add the exponents, gives us a value of 11, and then we add back on the 127, which gives us a value of 138. But we're not finished with this yet, because if you were to look now at the multiplication of the mantissas, this is the multiplication tree here, and this is the final 48-bit number at the bottom, and these are the two most significant bits. And you can see here the most significant bits start off with a value of a 0 and a 1. Now the full stop is at this point here, but we know that if we want to get a normalized number, the number must start with a value of 1, so it must be 1 point something. So in order to do that, we're going to have to shift the decimal point from this point up to this point here. That's a value of 1. So we're adding on a value of 1 here. So it means now that the mantissa is actually going to start from this point. So the mantissa is going to be given by 0, 0, 1, 1, 1. And you can see that up here. 0, 0, 1, 1, 1, and so on and so forth. But that value of 1, which we added on here, also has to be added on to the exponent. So that gives a value of 138 plus 1 is 139. And if we change the 139 back into our binary value, we get this value here, and that's the value you see up here. So the previous one there was no shift, but in this one here there is a shift. So let's finally look at the value 1 and 1. But first of all, before we do that, we'll have a look at this in the tool. So we're going to go put in our 50 times our 100, and that gives us a value here, and this is the value that we were looking at. So let's go ahead and we'll see what it's like when we look at it in the multiplication tree. So this is the multiplication tree here. And we can see here that our top two numbers are going to be a value of 1 and a value of 0. And we've already talked through all the rest of the values that you get from this. So let's move on and we'll look at the option wherever the possibility of getting a 1 and a 1 on the two most significant bits. So let's look at the third example of multiplying together a normal with a normal and getting a normal result. Let's look at the example of 500 times 500. It gives us 250,000. So I've put those values into the calculator here and it's given us the 32-bit result at the top. We work out our exponent as usual. We're going to have 135 and 135 in both cases because they're both the same numbers, 500 and 500. We subtract the 127 to give us a value of 8. Subtract 127 to give us a value of 8. 8 plus 8 is the value of 16, plus the 127 back on gives us a 143. Now if we look at the little bias section, see here we've got a bias here of 1. What we have to do here is we look at the decimal point, which is at this point here, and what we want to do is ensure, in this case here, that the highest value of our 48-bit is the value of 1. So we shift this point here again 1 over to the left. So we'll have the value of 1.111. So it means that the 11101 will now become our mantissa, and you can see that here. Now we've got our 11101 and then so on and so forth. So that value 1 gets added to the 143, gives us a 144, and when we convert it back into a value for our binary, we get this value here, and that's the value you see above. So in this instance here, the 1 behaves exactly the same as the 10. We have to shift the decimal point from here up one value to here. But the very first one we did, we had a value of 1 in here and a 0 here. So we didn't need to shift the decimal point because this value here was a 0. And we just want to make sure that the highest value that we have is a value of 1. So in that instance, the decimal point just remained here. So that's all of the cases dealt with, other than the case of a 0 and a 0. But if we're multiplying two normal numbers together, we will never ever get a case where we have a 0 and a 0. So we don't need to test for that. So that's all there is for this video. In the next video, we'll look at the case whenever we multiply together a normal number and a normal number and we get a subnormal result. Thank you for listening. Get you in the next video. Goodbye.